Alright, so this problem isn't so bad. We have a basic reaction here where we have HNO3, nitric acid, and potassium hydroxide reacting together and neutralizing each other to make a salt and water. And anytime you've got two strong acid and base combined, you get this neutralization that makes water and an ionic salt, something like this. And we did the first two of these in class, and I just typed them out here, and we don't really need to go through them too long. The first question asks 65.2 milliliters of aqueous HNO3 given a pH. Honestly, the 65.2 matters for the next part of the question, not the first. Anytime you're given a pH, if you're looking for concentration of hydrogen or hydronium, you just take 10 to the negative pH, and it's going to poop out what you're looking for. So 10 to the negative pH in this case gives you our 0.75 molar solution, and that's really all there is to it. We're going to need that later on in the problem, but in terms of this question, it should be pretty much instant. You see, okay, pH, H plus, run the calculation. For the second part, I'm asking about a titration, and at least for the final, whenever you see the word titration, and remember, titration is just that step of adding drops of acid to determine the strength of an unknown acid or base. Whenever you do that, you should think, okay, the equation is going to be this MAVA MBVB, and that's on your equation sheet if you look back on the one I gave you. And this equation is pretty easy. The A stand for acids and the B stand for bases. And so you say, okay, well, I've got MA because MA, I've already found that. That's the 0.75 molar solution from up top. And volume A, wait a minute, I've got that too because that's up here. You see 65.2. And molarity of the base, yeah, okay, I've got that because it was given here. And so I'm only missing my volume of the base, is what I'm asked. I'm asking how many milliliters must be added. And so you just plug in the values and you quickly solve and you get, well, 48.9 milliliters. And it's in milliliters because, of course, the volume I put at the beginning's in milliliters. If I had put in liters, I would have gotten liters. If I put in unicorn farts would come out. The units stay the same in this. And so I think these two make pretty good sense. And I think where people get a little bit concerned is, well, what about adding in excess? So I know from part B that I need that 49 or 48.9 milliliters to get rid of all the acid. But I added more than that, so I know that I should get a basic solution thereafter. So I had 65.2 milliliters of acid before I did anything else, right? So I had this acid going on, and that was like in my beaker here. Oops, where'd it go? Yeah, and there's like acid in here. There, that's acid, can't you tell? And on top of that, I added in my base, which I guess that's a B. Okay, well, those two things combine. And when those two things combine, they still fill up the same amount. I'm just mixing them in a container. So the volume is just the 52 milliliters of base plus the 65.2 milliliters of acid I was given in part 1. And I combine them together and I get 117.2 milliliters, which is actually 0.1172 liters because liters are way more useful in molarity calculations, and that's what we're going to be doing. My basic strategy is going to be to find the hydroxide ion concentration because I can find pH or POH from that. And if I can find POH, I can find pH. All of the hydrogen is going to react with all of the hydroxide until it perfectly makes water. And that's what we calculated in part B. That's what we calculated here at the 48.9. And so what I need to do now is say, well, okay, but I used some extra acid here, or extra base here. So how much extra do I have? And of course, I just subtract the two in here. And it tells me, okay, well, I got 3.1 milliliters of 0.1 molar KOH. And so how much extra hydroxide do I have? And so I use the definition of molarity, and I come through and say, oh, actually, I only have like 0.00031 mole of hydroxide extra. And because this is all 1-to-1 ratios along the top, and that will be what you get on the final if you do one of these, you're going to have just this concentration of OH as well. So you say, okay, I've got this many moles, I've got this much total solution, I just divide them through, and voila, I have a concentration of OH. And this is the step that's kind of hard, I get it. You'll only hear this is a little confusing, but work through it for a little bit, and I think you'll see that, okay, this actually makes good sense. And from here, it's easy. I've got a concentration of hydroxide. I need to get a pH. I need to take the negative log. That gives me the pOH. I need to take 14 minus the pOH, and voila, here we are. Ooh, I can't click out of that. That's annoying. Well, here we are, and I get 11.42, and that should be my final answer. There's no units on pH. It's a base. It's more basic than water. This fits my understanding. It's not a particularly strong base at 11.42, but it's there. But I mean, I don't expect it to be very strong. I only have 3 milliliters of relatively dilute potassium hydroxide in a tenth of a liter of solution. I mean, it's going to be a relatively weak base at this point, and that's what I get. So that's kind of how you do this. Take a look at the notes I sent you in addition to the video, and I think those two things together should make things pretty clear. Good luck.